Okay, let's get started. Today's colloquium is by Professor Xiaoming Mao from the University of Michigan. Her topic is on geometric frustration, self-assembly mechanics, and pathway to complexity. So her research can be broadly characterized as this emergent elasticity field. People try to understand mechanics from topology, from this a more general ideas. Okay, so this field, if we really want to look back, we can think of how we understand elasticity to begin with, and the idea was to understand a crystalline lattice, and from that, in Ashcroft and Mermin, we learned the everything can be understood from a periodic structure, and then the deviation from the periodic structure. So then everything then can be written down as a excitation from the symmetry broken ground state. From that, we can do a statistical mechanics. And then later we realize actually you don't really need a symmetry breaking in the phase transition, so that our own Kostelis-Thalès, Professor Kostelis received the Nobel Prize with David Thalès for understanding, for introducing topology into statistical mechanics. From that, we understood that there can be a phase transition in systems without broken symmetries. Ever since, and Duncan Haudet introduced the topology into quantum mechanics, and then now we try to understand elasticity from the topological constraint. So today, Professor Mao will tell us the current status of her field of this area. And Professor Mao got her undergraduate training from Peking University in China, even though her name is the same name of the guy on Chinese currency, but she promised that she has nothing to do with him. And then she did, like me, come after undergraduate, would come to America to study for graduate school. She went to Urbana-Champaign to do PhD with Paul Goldbart. And then she went to University of Pennsylvania to do a postdoc with Tom Lubinsky. And then she joined the University of Michigan, I guess a decade ago, or maybe a little longer. And then she has been there ever since. She's now a full professor from University of Michigan. She recently received, so Brown administrators always want us to get a grant. She got a $7.5 million grant from the Navy. So, so that's a largest grant I've heard so far. Okay, in condensed matter physics. Okay, so today we will hear about the her research.
Okay, thank you very much for the introduction. Can everyone hear me okay? Hello? Okay. that's closer, but when I wear it here, okay. Yeah, it is my great pleasure to be here today, and I really enjoyed all of the inspiring discussions I had today, and I look forward to talk to more of you after the talk. So today I'm going to talk to you about some of our recent work along the lines of studying geometric frustration, how they play their role in self-assembly and mechanics problems, and how geometric frustration offer us with pathways to complexity. So to begin, I'd like to show you some pretty pictures from nature. So let me see. Oh. Yeah, it is working. It's just, it wants to do an update. I'm sorry. Okay. No, I have to quit. Okay. So, okay, now it's working. So to show you some pretty pictures of nature. So what you're looking at here are these little structures you can find at the bottom of the ocean. They are called coccoliths. The scale bar here is 2 microns. So these coccoliths are made by single-celled algae called coccolithophorus. And coccolithophorus take calcium from the ocean and make them into these little armors to protect themselves. The main chemical component here is calcium carbonate. So we typically think of calcium carbonate as a boring material. We use that to make a chalk to write on the blackboard. However, in the hand of biology, they can take all kinds of intricate, beautiful forms, like these chiral plates, the minimal surfaces, regular dodecahedron, and all of these complex hierarchical structures. And these are definitely not singular examples. If you go to the biological world, there are many beautiful hierarchical structures. 2 more examples are our hair and the bones, which at the macro scale may appear to be some homogeneous and boring material. However, as you zoom into their microscopic structure, from the molecular scale to all the way to the macro scale, you can see that there are several hierarchies of complex chiral self-assembled structures. So how these structures form, what kind of purpose do they serve in biology, and why do they have to be so complicated? These are many interesting questions we can ask from the physics point of view. Before going into the details of these questions, let's first think about a more basic question. So what do we really mean by structural complexity? What do we mean when we say the structures of these materials are more complicated than some other materials? To think about that, let's just start by thinking about 2 extreme limits. In one limit, you have ordered materials, such as this crystal lattice, and in another limit, you have fully disordered, uncorrelated disorders, such as gases. If you measure the complexity of these materials using simple measures such as information entropy, you may say that this is much more complicated than this, because information entropy basically measures the total information content, and basically how much space does it take on your hard disk to completely record such a structure. For a periodic lattice, you just need a little bit of space because you can periodically generate it. But the fully disordered structure, the amount of information is proportional to the system size. However, although there is a lot of information here, not all of the information is useful. We can often write effective theories for most of the phenomena we see for these disordered materials. Most of the information is actually irrelevant. However, between order and disorder, we know that there are certain problems and systems that cannot be described by simple effective theories. They are truly complicated, and these pictures speak for themselves. So in order to capture such notion of actual complexity, this concept called effective complexity has been proposed. And to my knowledge, first by Nobel laureate Murray Gell-Mann, who wrote this book and talked about effective complexity that captures the non-random information in a problem or in a material. So for the examples I show here, they are from nature, and it has actually been argued that our nature runs in such a Goldilocks zone where the system has peaks in effective complexity, and that enables the best efficiency, robustness, adaptability, and multifunctionality. And for these examples, you can see that they are from nature and they are perfected through many generations of evolution. For us as physicists, one interesting question we can ask ourselves in relation to this is, can we assemble such complex structures in the lab without the biology? For example, using inorganic nanoparticles. Or another way to think about this question is, are these complex structures hard-coded from the biology, where you need genetic information to tell you where exactly to put each building block? Or you just need a little bit of genetic information, and the rest of the work can be automatically done by physics, geometry, and chemistry. So how do we think about that? Right? So let's come back to these two extremes, order and disorder, and think about how do we actually continuously go from one to another. From the physics point of view, we know that there is a simple pathway. You introduce more and more disorder into an ordered system. You can put in topological disorder, green boundaries. As you do enough of that, you can go to the disordered limit. Okay? However, that is, of course, not the only pathway. It's a huge dimensional space that you can go from this to this, because the system size is very large, and you can do many things to an ordered system and bring it to disorder. Another well-studied pathway in physics is to go out of equilibrium. You can have pattern formation, turbulence, and many interesting out of equilibrium process that give you a pathway between order and disorder. And of course, there is also biology, and we know all kinds of interesting complexity arises. The pathway I would like to talk about today is a pathway through geometric frustration. And we will show that geometric frustration actually gave us a continuous tuning knob that you can go between order and disorder and study some properties perturbatively and non-perturbatively. So what exactly do we mean by geometric frustration? So when you talk to a physicist and mention geometric frustration, this is usually the picture that comes up, where you have antiferromagnetic interactions on a lattice, where you have faces of odd-numbered sides, and then this spin doesn't know which way to point. That is a geometric frustration. Okay? The type of geometric frustration I'm going to talk about today is a more purely geometric concept. It is just a geometric frustration of packing shapes. So here I'm showing you 5 regular polyhedra in 3-dimensional space: the tetrahedra, octahedra, icosahedra, cube, and the dodecahedron. Can they pack 3-dimensional space? So maybe I can give you a quiz. Out of these 5 shapes, which ones can form a crystal in our space with no gaps or overlaps? The cubes can do that, right? Do you think anything else can form a crystal of 100% volume fraction? So I'm talking about 3D, right? So these are 3D, and I have to fill 3D space with these shapes. The octahedra, yeah. So it turns out that none of them can. All of these are geometrically frustrated. So how do you think about it, right? You can look at it by asking what is the dihedral angle, right? Because if you wanted to fill space, the dihedral angle better to be 2 pi over an integer, right? So that you can fit integer number of them around, yes?
Does that also include things like quasi-crystalline tilings?
So yes, so far, I think including both ordered and disordered and quasi-crystalline, there is no known 100% tilings of these other shapes. And you can really see it from the geometry. For example, taking tetrahedra, the dihedral angle is slightly smaller than 2 pi over 5. So you can fit about almost like 5 of them, almost 2 pi, but you have a small gap. And you can take 20 of them, almost forming an icosahedra. But again, you have these little cracks. And even if you can add a little bit of interaction or something to close the gap, you know this kind of five-fold rotational symmetry cannot exist in crystals in 2D and 3D. Okay? Although you can do it with quasicrystals, but the angles don't completely close. Okay? It's a similar story for all of the other shapes. So this is the type of geometric frustration we are talking about. Okay? So, of course, geometric frustration is a concept that has been studied a lot in condensed matter physics. It shows up in many different forms. For example, there has been theories for glass transitions and liquid crystal blue phases based on geometric frustration. And these concepts more recently has also been studied in the context of self-assembly problems. You can consider you have building blocks that don't quite fit together, and you can ask what kind of assembly you're going to get. And a lot of study has been done in estimating what kind of self-limited shape the clusters can form with geometrically frustrated building blocks. So the sort of new question we would like to understand here is about the relation between geometric frustration and complexity. To think about how geometric frustration can be used to control the system to deviate from the tendency of forming crystals and get controllably enumerate more structures. So that is sort of the question. So how do we think about why geometric frustration even relates to complexity? Here, I would like to show this figure from this recent paper where the authors try to study physical foundations of biological complexity. And this axis is complexity of interactions, and this axis is level of organization. So the authors argue that one origin of biological complexity comes from frustrated molecular interactions, where you have protons and other molecules with attraction and repulsion. And then when they come together in biological processes, you get glassy dynamics, self-organized criticality, and eventually, across the length scales, get the complex biological systems we see. So again, from a physics point of view, if it all starts with frustrated interactions, we can also take these molecules and see what they do in the lab, right? However, typically what we get if we, say, cool down the system slowly, they eventually make a crystal. The tendency of having long-range order will overwhelm the frustration, and you get a compromised structure, which are crystalline. Or if you cool down quickly, you get a glass. Why don't we get these interesting stuff in the middle when we take the same type of molecules in the lab? So to be fair, I should mention that in the inorganic world, there are also rather complicated structures, such as the geometric shapes of snowflakes or diffusion-limited aggregation. However, the formation of these structures usually require well-controlled out-of-equilibrium conditions. And the question we would like to discuss here is, by making use of geometric frustration, can we control how the system deviates from the tendency of forming crystals? Can we make the formation of these complex structures more inevitable and controllable and programmable, per se? So this leads us to the outline of my talk today, where we will first talk about this recent paper we wrote on frustrated self-assembly of non-Euclidean crystals of tetrahedral nanoparticles. And this was done in collaboration with my former postdoc, Francesco, my colleague, Nick Kotov, and his postdoc, Jun, and also my colleague, Kai. And I would like to also acknowledge discussions with Sharon Glotzer's group, her postdoc, Philip, student, Yeyin, and my graduate student, Nan. And after that, if we have more time, I will also talk about our recent papers on mechanics of frustrated and non-Euclidean systems, basically trying to answer the question, why do we want a frustration when we can get crystals? Why do we need all this complexity? Okay, so let's start from the first part. I would like to first describe an experiment that inspired us to think about this problem. This experiment is from Nick Kotov's lab, where they take semiconductor nanoparticles. Here, the particles are about 5 nanometers in size, And these are crystalline particles made of cadmium telluride. And the surface of these particles are covered by chiral ligands, which are these organic molecules that can bind with one another. So they put these nanoparticles in solvent, and the particles come together and the ligand bind and they self-assemble. And they get all kinds of complicated shapes from the self-assembly. For example, these chiral crystals. And the scale bar here is about 2 microns. So you can see that this is a spiral that is much bigger than the original particle. And by changing conditions, they also get all kinds of complicated products, such as these bow ties and bundles. And with other similar nanoparticle plus ligand systems, they also get all kinds of shapes, such as hedgehogs, and these are what they call kayak particles and complicated shapes. So when we first look at these pictures from this experiment, what really strikes us as condensed matter theorists is really, where is the complexity from? You start with really simple building blocks, here regular polyhedra, and yet you get all these complicated shapes coming up. Where is the complexity coming from? So to understand that, let's look at the geometry of the problem again. So as I mentioned, packing of tetrahedra in 3-dimensional space is geometrically frustrated. You can actually make 1D chains of tetrahedra with no frustration. You can just attach them face to face, you get a helix. And there are left-handed and right-handed versions of these tetrahelices. However, when you try to put these tetrahelices together, there is the frustration because, as I mentioned, the dihedral angle don't add up to 2 pi. There will be a small gap and they split further and further away as you go out. Okay? Interestingly, this geometric frustration, if you think in terms of a geometric point of view, they are an artifact of the flat 3-dimensional space we live in. If you are able to introduce a little bit of curvature into our 3-dimensional space, you can actually close these gaps and get a perfect packing of these regular polyhedra, in this case, tetrahedra. So this is rather abstract to think about. What does it mean to introduce curvature to 3-dimensional space, right? So to show that, let's first look at a 2-dimensional example where imagine you have a bunch of pentagons and you try to use that to tile the floor. And obviously, we all see it doesn't work because the interior angle is smaller than 2 pi over 3, but bigger than 2 pi over 4. So you get these gaps. However, you can introduce curvature to close these gaps. So here I have a video to show how that works. If you curl it up, you can close the gap, and what you get is really a regular dodecahedron, right? And this is a perfect crystal in the sense that the local environment of every vertex, every edge, and every face is all perfectly the same. The structure looks perfect in 3D, where all of the nodes live on the surface of a sphere in 3 dimensions. It's a so-called two-sphere. And when you project it to flat 2-dimensional space, you get this structure which looks very distorted. However, the actual structure in 3D is perfectly ordered. Okay? So this is an intuitive way to think about it, and now we can look at the analogous process in 3 dimensions. We can take the dodecahedron that we got from the last step and try to pack them in 3-dimensional space. And again, the dihedral angle here is slightly smaller than 2 pi over 3, so they don't quite fit together. You get these little gaps. This video nicely demonstrated this process. So you get a 1D chain with no frustration, and when you try to bundle these chains together, you can see they twist around each other, and then there are small gaps. However, you can take 2 such pillars, each of 60 dodecahedra, and put them next to each other, and you introduce a little bit of positive curvature. By introducing this positive curvature, you close the gaps. but at the same time, the chain is close to itself because it's an isotropic curvature. And in the end, you get a finite crystal, which is a so-called 120 cell. It's a regular polytope. So polytope is a generalization of polyhedra to higher dimensions. This is a structure that perfectly lives on the surface of a ball in 4 dimensions. And the picture here looks distorted because we are projecting from 4 dimensions to 3 dimensions. The actual structure in 4D is perfectly ordered. Every dodecahedron is the same. And they just appear to be like this because I cannot show you a 4-dimensional picture. Okay, does it make sense? Any questions? I will just show this video again because it nicely illustrates the geometry. Okay, so here, all of the nodes live on the surface of a ball in 4 dimensions, which is a so-called 3-sphere. Okay? And here I have positive curvature, which is isotropic and homogeneous everywhere, and I get a finite-sized crystal. Okay, so this is a video of dodecahedron making 120 cell. What happens with tetrahedra, which is the particle we are studying here, is very similar. I don't have a nice video to show that, but what they make is a so-called 600 cell. And it is analogous, it is actually due to the 120 cell. They are very similar. They both have positive curvature, and they are due to one another in the sense of polyhedra duality. So these are mathematical concepts that has been known for decades, right? And you can even find architecture and sculpture taking this concept as an inspiration. This is a picture I took in Toronto earlier this year. So why do we think these are relevant for self-assembly problems or other types of soft matter problems? The reason we think they're relevant is because they actually represent the true energetic ground state of the problem. Why we say it's a ground state? If you think about a tetrahedra packing into this so-called 600 cell, when they pack in this way into 600 cell, you get a perfect face-to-face alignment, and the whole thing has 100% volume fraction. So it is really the minimum of the potential energy if you have shorter range attraction between the particles, right? So they are really the thermodynamic ground state of the problem. Then to show the thermodynamic relevance of such a ground state, although this ground state doesn't live in our space, you require curvature, right? I would like to quote this Monte Carlo study from the 1980s, where the author actually ran Monte Carlo simulations of sphere packing on the 3-sphere. Remember, the 3-sphere is the surface of a ball in 4 dimensions. It's actually a solid structure, right? It's 3-dimensional, but on 4D, it is on the surface of a ball. So anyway, the sphere packing on the 3-sphere is very similar to the 120 cell because you can imagine each sphere occupying the space of a dodecahedron, okay? And what this paper found was that when you run Monte Carlo simulation on the 3-sphere, the system really quickly quenched to the ground state, which is the 120 cell. In contrast, when you run Monte Carlo simulation of sphere packing in flat 3D space, we know that the ground state should be a FCC lattice. However, if you have run the simulation, you know that it takes forever to anneal out all of the defects. And it takes a very long time for the system to relax. This is a vivid demonstration that this structure in flat 3-dimensional space is frustrated, but it is happy on the 3-sphere. That is the space where it naturally packs, okay? So in this study, it forms completely different structures on the 3-sphere and in 3D Euclidean space. The new question we would like to explore here is really, can we take a part of these non-Euclidean crystals because they are these nice ground states, right? Can we realize part of it in our space in self-assembly problems? And if that works, what kind of morphology do you get? And what kind of complexity comes out of these assembly problems? So this is basically the analytic theory we try to build in this paper. And here, without getting into too much details, I will just sketch out a few steps of how it works. Basically, we start from this non-Euclidean crystal, which we believe to be the true ground state energetically, and we take that as our ideal metric, and then use that to build a continuum theory to study self-assembly in Euclidean space perturbatively. So we start from these non-Euclidean crystals. The first step is to understand their internal structure, right? So we actually know who is whose neighbor, right? This happens to be a well-documented problem in mathematics, so we can just quote known results. Basically, for the case of the 600 cell, it can actually be decomposed into 4 toroidal shells. Each shell has 150 tetrahedra. You can basically decompose them into 5 tetrahelices that are intertwined to one another. And then these different toroidal shells are linked to one another. And this is a figure that shows their topological structure. It's really interesting to look at. The next step is to find a coordinate system so that we can label all of these building blocks and describe them mathematically. So here we choose a 3-dimensional coordinate where we have 3 directions. One direction goes across the different shells, and then we have 2 coordinates that are in plane. In particular, the beta and theta directions are along the left-handed tetrahelix and the right-handed tetrahelices separately. In fact, when you look at this structure, you realize that you can either color them according to right-handed helices or left-handed helices. The 600 cell itself is achiral, but you can decompose it in chiral pairs. Okay? And then you can embed the whole thing in 4 dimensions, and you can check that all of the nodes are on the 3-sphere. And then we have a mathematical basis now to construct a metric tensor, which is our ideal metric. And here you can see from this metric tensor that it takes a rather simple form. It really carries the information of the ideal distances between these tetrahedra of their perfect packing, of what they want to be to minimize their energy of interaction. So you have an alpha direction that is always perpendicular to the in-plane directions, and then these other 2 directions rotate as you go across the thickness direction. That is the main mode of geometric frustration here. And you can calculate the curvature and verify that it has a homogeneous isotropic positive curvature. And then the next step is to cut a slice of this non-Euclidean crystal and try to take it to our space. So why do we need to cut a slice instead of taking the whole crystal to our space? It is really because that the whole crystal is going to be super stressed. It is similar to this 2D analogy. If you take this whole dodecahedra and try to squeeze it to 2D, it's super stressed, right? You can see that this one is a nice pentagon, but all the other pentagons on the edges are stretched. Okay? It's the same when you take the 600 cell and try to squeeze the whole thing to our flat 3-dimensional space, it's going to be very stressed. However, if you just take part of it as a thin sheet, you can actually have low energy solutions. Okay? So here in particular, we take the 2 middle toroidal shells, where the reason is that they gave us 2D smooth surface, so we have low surface energy, and the ideal metric doesn't depend on the in-plane coordinate. So we really have the same connectivity for the in-plane directions. So this really allows a high yield of the self-assembly problem. So then, when we take this, we can calculate what kind of morphology this thin sheet is going to bend or twist in our 3-dimensional space to minimize the energy. So I will go quickly through some details. We can write an energy that include all of the interactions in the problem. Elasticity, electrostatic repulsion, the particles are charged, and the binding energy and the boundary energy. When we choose a particular slice, these binding and boundary energies are already determined. So what determines the morphology are these first 2 terms, elasticity and repulsion. And for elasticity, it is really coming from a strain tensor. where the actual metric of the assembly cannot take the metric it wants to be, because the metric it wants to be in terms of energy is not Euclidean. And the actual metric, because it has to be in our space, must be Euclidean. So there is a deviation, and that enables us to write a thin shell expansion and have a continuum theory. And then when we also include the repulsion energy, we can put it together with the elasticity and minimize them simultaneously. We can find the shapes that minimize the total energy. It is never zero because it's frustrated, right? So it turns out to be very similar to this known problem of frustrated elastic bilayers, where each of the layers want to contract in different ways. And we find that the regime of solution our system takes is in this regime so-called bending-dominated elasticity, and the final solution takes the form of helicoids. We can calculate the pitch of the helicoid, which is controlled by the computation between the electrostatic repulsion and the elasticity, the frustrated elasticity. So we can then take this and compare with experimental observations. So in the experiment, they can change the solvent properties which control the electrostatic repulsion, and they can get different morphologies. And then they can measure the pitch of these helicoids, and we get some qualitative agreement from the prediction and the measured morphologies. And currently, we're collaborating with Sharon Glotzer's group to run molecular dynamic simulations of these nanoparticles to see what kind of kinetic pathways these particles actually find each other to build these non-Euclidean crystals. And this is one example of the simulation. You can see that this structure is perfectly ordered. There's no disorder, and yet it is an order that is not allowed in Euclidean space. So the structure actually splits, although this is a perfect triangular lattice on this surface. Okay? So it is really the interplay between frustration and attractive interactions and repulsion between the particles. And we can get a little bit of analytic theory control of understanding this process. Okay? So this is the first system we looked at, and then we went on to think about what happens to other types of polyhedra, right? So we mentioned there are different types of polyhedra, and they can tile space of different curvature, really depend on how many of them you try to fit around each edge. Here, taking tetrahedra, if you try to fit 5 of them around an edge, you need a little bit of positive curvature to close the gap. And if you try to fit 6 or more around an edge, you need a negative curvature to get rid of the overlap. So they can either assemble on S3, which is 3-sphere, or H3, which is hyperbolic 3-dimensional space. And that's similar to what happens to all of the other types of regular polyhedra, either in H3 or S3. So for all of the cases where you can get a non-Euclidean crystal in the 3-sphere, the theory is going to be similar because you always have positive curvature and you can write the same type of continuum theory, just with different types of, different amount of curvature. However, what happens with hyperbolic space? So to understand that, we choose to also study the self-assembly of icosahedra. Icosahedra is a special one compared to all of these because it has a really large dihedral angle. Even if you just try to fit 3 of them around an edge, they are already overlapping. So they never assemble, they never tile S3. They can only tile hyperbolic space, so you always have negative curvature. And although it seems just a change of sign, the nature of S3, the 3-sphere and the hyperbolic 3D space is very different. In particular, the hyperbolic 3D space is actually infinite crystal. You introduce negative curvature and you get an infinite crystal of non-Euclidean metric. And in this case, for icosahedron, what you get is actually the so-called 353 regular tiling. And what I show here is a picture of the so-called Poincare ball projection. So you bring the infinite crystal to a unit sphere, and it again looks very distorted because it's a projection. It's a perfect crystalline structure in hyperbolic space. And the icosahedron from infinitely far away map to infinitely small structures on the edge of the unit sphere. And then we can do a similar calculation starting from this and cut apart a slice of the crystal. In particular, we cut a slice with zero Gaussian curvature and then find the icosahedra that intersect the surface and use projection to find the energy minimizing structure, and then put the icosahedron back, we get a prediction for the assembly. In particular, here is an interesting spontaneous symmetry breaking problem, because when you try to find the structure that minimizes the energy, the solution depends on the size of this disk. For small disks, it is dominated by bending energy, and you get a spherical disk like this. And for larger disks, it is dominated by stretching energy, and you get this taco-like shape. So you have to choose a special direction, and we can characterize this spontaneous symmetry breaking. And we have yet to see experimental verification of this theory, so far it is just a theory. So anyway, to summarize the first part of my talk, we discussed using non-Euclidean crystals as a guiding principle because they offer us with a ground state, and we can use that to study the self-assembly of these geometrically frustrated building blocks in Euclidean space. So basically, we follow these steps and predict the stressed morphology. So in the beginning, we talked a lot about complexity, right? So we haven't really studied the actual complexity. We just say that it's going to offer us complexity. So let me expand on that just a little bit. Firstly, what kind of polyhedra packing rule should we actually use? For the case of tetrahedra, it's kind of obvious because 5 of them almost closes. But depending on the interactions between the particles, there can be a lot of other ways you could pack them. These packing rules can give you all kinds of non-Euclidean crystals. So there is a lot of mathematical complexity in this problem, and you can also introduce topological defects. And there is a realm of different types of topological defects you can have in these non-Euclidean crystals. And the second part, where you can get a lot of complexity, is really the statistical mechanics of the problem. So far, we haven't talked about any statistical mechanics. All we did was just minimization. However, the real system is thermodynamic. You can have equilibrium and out of equilibrium fluctuations. How do you put statistical mechanics together with these non-Euclidean structures is a whole question that has been rarely studied. And there's also the step of which part of the non-Euclidean crystal we should study, and how you cut it can happen in many ways. We have a computation between surface energy and the natural tendency for the structure to split and crack due to stress. So a lot of interesting morphology could show up that become similar to what happened in biology. So basically, we argue that there is this interesting design space, which we call a non-Euclidean design space, you can use to predict the self-assembly of frustrated building blocks and use that to program complexity. Okay, so this is the first part of my talk on self-assembly and geometric frustration. So any questions before I move on to the next part? Yes?
Why just like 4 dimensions? I don't really understand whether is that just because your point is that this 3D structure can be understood as a perfect tiling in a higher dimensional space, right?
Yeah, that's a.
Why do you stop at 4D? Couldn't you think about higher dimensional things that fold into 3-dimensional objects?
That's a great question. So it happens that 3-sphere can be embedded in 4D. However, H3 cannot be embedded in 4D. So 3-sphere has this nice property that we can start from a 4D embedding, and all of the metric you can just induce from 4 dimensions. But H3, you can actually not do that. And the theory doesn't really depend on 4D. It just happens that the first example we calculated can be done in 4D. Yeah. So because what we really use is this ideal metric. And this ideal metric could be embedded in 4D or higher dimensions, but we just take that as an input for the continuum theory. Okay. Okay, so yes.
For the tetrahedra in S3, is it
Yeah.
possible to realize that the other regime, where I think it was, instead of like the helicoids, it was the, I don't know what you call that other shape.
The bundles.
Yeah.
Yeah, that is possible. So basically, we just studied the simplest case in our first paper, but you can cut it in different ways. You can actually take other sections of the 600 cell, right, and study its morphology. I think the bundles could also be rather conveniently studied theoretically. Basically, if you can find a thin structure, either 1D or 2D, you can do expansions, and then it can be analytically solved. Yeah. Yes?
Maybe related question. So you said, so you can take different cuts, right? So essentially you have to take all the cuts to compare their energy, like in like Euclidean space. Is that what you do? Or
Right, so it is actually very hard to get all of the cuts, right? Because there are so many ways you can cut. So our first study is basically guided by the experimental observation because they see thin sheets, so we cut a thin sheet and see what happens. But yeah, you can try different cuts, and we're pretty sure that this is one of the lowest energy states because it has a small surface, and it has one direction that is not frustrated. And then it grows a little bit of width in the other frustrated direction. But yeah, it is unknown how, like, are there other better cuts and how that interplay with the non-equilibrium assembly process. Yeah. Yes?
Regarding the Monte Carlo simulation of a structure that
Yeah.
we know the exact solution. So what's the motivation for the Monte Carlo is to see which one is the kinetic pathway?
Yeah, to see the kinetic pathway. So we actually learned a lot from doing these simulations because the analytic theory solves for the final minimizing energy solution, but we don't know if the system can actually find, the particles can actually find each other to form that. So it turns out that as we tune parameters in the Monte Carlo simulation, we find that we need it 2 stages. It first form these tetrahelices, and then tetrahelices combine. We cannot find a parameter regime that it just one step form this ribbon.
So don't you have to cheat a little bit in the Monte Carlo that to guide the system?
We
If you do a blind Monte Carlo, then you will never convert.
we haven't been able to just do it one step. We need to tune the parameters so that you get a chains and then the chains combine. Yeah, exactly. Okay, so if no more questions, I will talk just briefly about the 2 recent work we have done in understanding mechanics in the setup of this non-Euclidean geometry. So the first study is really inspired by thinking about the different types of geometric frustration. So in frustrated magnetism, it is known for a long time that you get many ground states, right? And out of these ground states, you can have extensive or sub-extensive degeneracy, and then from this degeneracy, you get a lot of interesting phenomena. You have a lot of tunability in breaking this degeneracy, and you get a new order and the new quantum states, new topological states. So then our question is, can we get the same type of thing in this kind of pure geometric frustration in packing or elasticity problems, right? What kind of dynamics are you going to get? So to study that, we picked a particular problem instead of packing, because packing is kind of harder to control. So we just picked a continuum elasticity problem, which is the thin shell elasticity. So this is a well-studied problem. When you have thin elastic bodies, you can expand the elastic energy into a stretching-dominated part, which is controlled by the in-plane deformation, and a bending-dominated and a bending energy part, which has to do with the out-of-plane curvature, right? And interestingly, there are compatibility conditions for the target structure for in-plane and out-of-plane, the so-called Gauss theorem and the Gauss-Kodachi equations. If you choose the reference structure for in-plane and out-of-plane to be incompatible with one another, you have a controllable geometric frustration. And you can get all kinds of interesting shapes. So this leaf is one example, because when each of the cell grows, it doesn't know about the global minimization, right? They just grow locally to biological rules, and you end up with geometrically frustrated biological shapes. So these papers, these...
But there's nothing wrong with that.
Nothing wrong, of course, nothing wrong.
That's where
right.
the diversity of biological systems comes
Yes, yeah. That's one way of thinking about it, right? So there has been well-developed theories to calculate this kind of shapes, right? So then we think like this may be a good system to study degeneracy, right? When you have frustration, you should get a degeneracy. So we chose a particular like analytic regime to do this study. We picked these so-called minimal surface associated families, which has a special feature that you have a set of shapes that has exactly the same elastic energy in the limit of infinitely thin ribbons. And this is so-called helicoid ketenoid family. You can label all of these shapes using one phase angle phi. So there is a U1 degeneracy. And when you have a little bit of thickness, you can actually break this degeneracy, so you have a U1 manifold of low energy states, and out of them, you have two particular states that are the minimum of the energy, which are the left-handed and the right-handed helicoids, okay? And then using this setup, we can write a low energy effective theory if you have a long ribbon governed by this elasticity. Basically, you have a gradient term. Remember, this phi is just the shape between helicoid and ketenoid. And then you have another term that favor the left-handed and the right-handed helicoids. So if you're familiar with theories of topological solitons, you can see that immediately this kind of theory has soliton solutions. And in particular, you can have solitons where the phase angle wind by 2 pi, or the phase angle wind by pi. And if you define the soliton charge by the change of the phase angle divided by 2 pi, you would say that this is a charge 1 soliton, these are charge 1/2 solitons. Okay? So then you may say, why do we name it this way? It turns out that there is a very interesting analog to these dimerized antiferromagnetic spin chains studied by Houdin in 1980s. So you can have these two dimer ground states, which are just shifted by one lattice site away. And then when you have this spin 1 excitation, you can move them apart. Each becomes a highly robust spin 1/2 excitation. But in between, the lattice is switched to the other ground state. That is exactly analogous to what happens to this simple elasticity problem. And then we can see that there is a lot of robustness in this kind of excitations. Yes?
Can you go back to the...
Yes.
So Houdin himself said that he got this idea from costless dollars to the unbinding of the pair.
Yes, there is a lot of relation there. Yeah. Right. Okay.
So do you have a KT transition here? Should we anticipate one?
That would be interesting to study. Yeah. We haven't. Right. So here I just want to mention the robustness of this problem. So some of you may be familiar with Sine-Gordon solitons, right? You can have a theory like this, but the only difference is this factor of 2. We have 2 ground states, and here you have only 1 ground state. And in this case, you can see that you always wind by 2 pi. And from far away, you can get rid of this soliton locally. You would not know it from far away, although getting rid of it locally is beyond the low energy theory. Here, because it separates 2 types of ground states, you can never get rid of a spin 1/2 excitation locally. Right? So this gave us a lot of robustness of this type of excitations, and which we can actually see in experiment. So what we did here is, in collaboration with Alan Aruda's group, we 3D print a helicoid. We print it in a right-handed helicoid, and then we can put it to the left-handed helicoid. The system actually has thickness So the left-handed helicoid is a metastable state. We twist it to the metastable state and release it. What happens is that the system generates two solitons by itself from the top and from the bottom, and they travel and meet in the middle and annihilate with one another. It is interesting to look at because this is made by rubber. It's a highly dissipative material. Normally, you would think a soliton would just die away, right? Because it's highly viscoelastic. However, this soliton cannot die because it's topologically protected. No matter how long this ribbon is, it will always go until it flips the whole thing to the ground state. And you can actually calculate the speed of this soliton. It's locked. Its speed is controlled by the conversion of elastic energy to kinetic energy. And there are interesting properties that we are currently making use of. For example, it flips the chirality, and it also gives you a holographic control, because when you twist the boundary, you can pinpoint where this soliton is. So basically, we argue that from the geometric frustration, you can control degeneracy and use that to generate fractional excitations and controllable robust dynamics. Okay, so the last few minutes, I'll just mention one last work where we try to study waves in non-Euclidean lattices. So this is one of the hyperbolic two-dimensional lattice, which is the so-called 7-3 tiling. So basically, you take heptagons and try to pack them together. There is too much area, so it can only be realized in hyperbolic space. And this is the so-called Poincare disk projection. So we already talked about that they can naturally show up in self-assembly problems. But then it offers us interesting new types of crystal, because we know that crystals in Euclidean space, you can only have you can only have finite choices of crystalline symmetry, right? We know from Bravis lattice and unit cells, there are finite types of crystal groups you can have. Here, you have infinitely many choices. You can have any symmetry because you can tune the curvature to accommodate any symmetry you want. And then this gave us many interesting properties. So this is one of the hot topics. Recently, people studied band structures in this kind of hyperbolic crystals, and you can have high-dimensional Brillouin zone, although the structure is actually two-dimensional, and you can have topological states. So what we tried to do here is to really extend Bloch theorem to these hyperbolic crystals. Basically, we all know that Bloch theorem is one of the cornerstones of condensed matter physics because it enables you to write wave bases for periodic systems. In Bloch theorem, we know because of the translation symmetry of the lattice, you can represent translation by a phase factor, right? And that greatly simplifies all kinds of calculations. However, for hyperbolic crystals, the translation group is non-abelian. So this tells you that there must be high-dimensional irreducible representations. In addition to complex phase factor, translation must also, you must also be able to find waves where the translation is represented by matrices. And in this paper, we showed how to systematically construct waves that carry these high-dimensional representation of their non-abelian translation group. And we can do interesting calculations, for example, finding band structures of hyperbolic lattices and show how edge waves could be represented in these kind of lattices. Okay, so now I think it's a good point to wrap up. We looked at geometric frustration and how they show up in self-assembly and the topological mechanical problems, and how they offer us for future studies with pathways to complexity. I'd like to thank my funding sources and thank you for your attention.
Okay, open for discussions. Yes. I need to give you the speaker because otherwise it won't be recorded.
Okay, I have two questions. One, I think, is just clarification. Both my questions are on your solitons. So can you clarify how you got from the U1 to the Z2? Was that just picking a particular parameter space, or does it spontaneously?
Right. So here, when it's infinitely thin, it's a leading order theory, and you have exact U1 symmetry.
Okay.
When you introduce a little more thickness, you can actually choose. You can actually basically you add a perturbation to this, and there are higher order terms you need to keep. That breaks the U1 symmetry into Z2.
Okay.
Yeah, the Z2 is really the two sides are the same.
Yeah. It's not like, I was just wondering if it was like an order by disorder where you'd have a sub-extensive degeneracy, and out of that spontaneously pick discrete.
Right.
States.
It's simpler than that.
Yeah.
So here it's just energy.
Okay.
Yeah.
And then my next question, actually, I'm just curious about this analogy that you made with the Haldane chain, the AKLT construction of the Haldane chain and the soliton lattice.
Yes.
So I'm just wondering, there are other simpler magnetic systems like a ferromagnetic chain in a magnetic field that has solitons.
Yeah.
That's totally classical. The model there is completely quantum. So I was just wondering if there's something else about these solitons that makes the analogy with the spin-1 chain more like deeper, rather than just you could also make an analogy with a ferromagnetic classical chain.
Yeah. That's a great question. So I think if I understand you right, you can say that you can just map this to spin up and spin down, and you also have this type of robust domain walls.
Right? You could have domain walls in a ferromagnetic chain, and
yeah.
those are solitons, but those are different than the excitations which you've written down there, which are the edge states of a spin-1 chain, written in terms of this AKLT construction where you decompose it into spin halves.
Right. I think it has to. I need to think a little more about the subtle difference. Yeah.
For instance, in the bulk, are there gapless excitations, or is everything gapped in the bulk? In the spin-1 chain, there are no gapless excitations. In the ferromagnetic chain, there are the gapless Goldstone modes.
Right. I think these are also gapless. Right.
So
you
it'd be
can
more
have.
classical.
You can have smooth.
Not the edge states, so not the defect states. The defect states are gapless.
Mm-hmm.
But then there are other excitations in, for instance, the ferromagnetic chain that are also gapless. Whereas in the Haldane chain, there are also other excitations, but they're gapped.
Yeah.
By the topological term.
Right. So I need to think more about that. I think here we are focusing on the dynamics provided just by this low energy theory. I think if this low energy theory also maps to other types of magnetic systems, then we can also make that analogy.
Okay.
Yeah.
Thanks.
Okay.
Actually, I have a follow-up question on Kim's question.
Yeah.
So I realized in your system, in this case, for classical thermodynamics, that you cannot have a KT transition because each of this defect is actually not topological. It's a topological defect, but actually there's no logarithmic term with the system size because it's local.
Yeah, it is local. Yeah.
Right, so you can't have a KT transition here. I understand, but I'm thinking of like a long-range IC model in 1D, you can have a phase transition, right? Yeah.
Yeah, so if you have fluctuations, I think you will have unbinding of
right.
these. Yeah.
Okay, any more questions? Geometric frustration. So if you have frustration, you know, the calendars have a frustration, right? So the one way to make one way to resolve the frustration is to create a holiday, right? So that's a topological defect. All right, let's thank Professor Mao again.
Thank you very much.